Hi everyone, in this video we are going to use a bunch of different bond energies in order to calculate the enthalpy of the reaction for a number of different chemical equations or chemical reactions. So before I even dive deep into these actual examples and these problems, what I want to do is just remind you of the very quick formula that you need to have at the front of your mind in order to do any of these problems in this video. So the first thing is, when we're talking about bond energies or bond enthalpies, recall that you're always trying to solve for your delta H of your reaction, for the enthalpy of the entire reaction. And the way we do that is by taking bonds broken and you subtract them away from bonds formed. Okay, so just to basically think about it, you have to break all of the different bonds in the reactants and then create all of the different bonds in the products. Okay, so that's how we're going to think about it. So what I've done here is come up with an equation or a chemical equation for you, and I've also provided this chart so that you can use these specific values when calculating your delta H of your reaction. So we've got hydrogen plus carbon dioxide creating water and carbon monoxide, and I would like you to determine the delta H of the reaction using these specific values. Okay, don't look them up on another table. We want to have the same answer here. All right, go ahead and try it. All right, did you get an answer? Hopefully you did. And the very first thing that you have to do is draw this out. Okay, so we know that we have one hydrogen. It is reacting with one carbon dioxide. And then it's creating one water. And it's creating one carbon monoxide. So if you can't even draw these Lewis structures, you have no shot of getting this answer correct, okay? So I need to make sure that you understand that, so hopefully you do, okay? So now remember, delta H of our reaction is equal to our bonds broken minus our bonds formed. So we're going to go through here and do that with this specific equation. So our delta H reaction, bonds broken. I have to break this HH bond, and this carbon-oxygen bond, and this carbon-oxygen double bond. So we're going to break a hydrogen-hydrogen. And we're going to break two carbon-oxygen double bonds. Yes, it is very important that you keep track of if it's single, double, whatever, okay? So bonds broken minus bonds formed. So we're going to create two oxygen-hydrogen bonds. And we're going to create one carbon-oxygen triple bond. Okay, so that is your second step. So first step's draw, second step's come up with this equation. The third thing is you need to substitute in numbers, okay? So if we go to this original chart, the first thing we're looking for is a hydrogen-hydrogen bond. So our hydrogen starts over here on the uppermost side, right here in the upper left side. And so we see a hydrogen here and another hydrogen here. So you just bring your fingers in, and wherever they meet, that's the value you use to actually determine these bond energies. So for hydrogen-hydrogen, I saw that it had a value of 436. These are all in kilojoules per mole, but I'm going to drop my unit just for simplicity here. For carbon-oxygen, we had to go find its double bond, so that's over here. Carbon-oxygen double bond is 799, so we have to put that one in. And then we have to subtract this away from our bonds formed. So we need an oxygen-hydrogen bond. So again, come over here in this top side. We see our hydrogens here on this top. And then we can come down and see our oxygen, which is about right there. There we go, 463. 463 for oxygen, hydrogen. And then our last one is our carbon-oxygen triple bond, which we can actually see right here, and that is 1072. So 1072. Again, everything's in kilojoules per mole. You should be writing this out as you go, but I'm kind of lazy and we're dropping it just for simplicity and room. So if you do this in your calculator correctly, 436 plus 2 times 799, okay, all that number, minus all of this, 2 times 463 plus 1072. If you do that properly, you should get an answer of about 36 kilojoules per mole. And you can always check your answer and say, would I expect this to be endothermic? Would I expect this to be exothermic? I absolutely would expect this to be endothermic, so a positive value, because we're going from a double bond to a triple bond. Triple bonds are notorious for being unbelievably stable, so it's not surprising to me at all that we end up with something that's about 36 kilojoules per mole. All right, let's try another example here. I'm going to make it a little bit more challenging because I've added some more coefficients here, so you remember you cannot drop those. So now here's your equation and here's your chart with the table of energies. So go ahead and just take a second and see if you can actually determine this one here for us, okay? Go ahead. All right, hopefully you were able to get this one. This was definitely a longer problem. You had to take some time and make sure that you draw out the proper structures. So the first thing we did is we needed to draw out methane. Okay, so here's our methane. And then we treated methane with 3 diatomic chlorines. So there's 1, 2, and 3. And then we said it created a CHCl, 3 Cls, 3 chlorines on this one. Okay, there's 1. And then we had 3 HCl species. There's 1, 2, and 3. Okay, so we've drawn everything out. Now we need to come up with our basic formula. So delta H of our reaction, bonds broken minus bonds formed. So I see that I break 1, 2, 3, and 4 CH bonds. I also am going to break 1, 2, and 3 chlorine-chlorine bonds. Okay, so those are our bonds broken. Now we need to subtract out our bonds formed. So we're going to create 1 carbon-hydrogen bond plus 1, 2, 3 carbon-chlorine bonds. Ooh, let me try that. Carbon-chlorine, so that's a carbon and a chlorine. There we go. Plus 3, so 1, 2, and 3 HCl bonds. HCl. All right, so now I showed you how to use the chart previously, so I'm just going to go ahead and plug these numbers in for the sake of time. So we should have 4 times 413 plus 3 times 242 minus 413 again, that carbon-hydrogen bond, plus 3 times 339 plus 3 times 432. Okay, so if we plug all this in together, we would hopefully end up with something of negative 348 kilojoules per mole. Would you expect for that to be exothermic? I personally would, because I know how that is. If you're doing something, if you're breaking apart carbon-hydrogen bonds, it has to be exothermic. I don't know that you personally would have the skills to be able to identify that yet. So if you weren't able to automatically look at that and say, oh, definitely negative, don't worry about that, okay? All right, let's do one more, and this is just a little bit trickier, even though the math is actually a little bit simpler, okay? So the reason it's more challenging is because I've only given you words, and so I'm telling you, please take nitrogen and hydrogen and create ammonia. Now, ammonia is one that I expect you to know, but if you've forgotten it, just for the sake of time, I'm going to tell you it's NH3. All right, so try this last one. All right, did you get an answer? Hopefully you did, and the first thing that you had to do was come up with a proper chemical equation. So we know nitrogen exists naturally as a diatomic species, so N2, plus H2, hydrogen's also a diatomic, and we're going to create ammonia, so NH3. So now we have our skeleton structure out, but this is an unbalanced chemical equation, so we need to balance it out. So I see 2 nitrogens, but only 1 on this side, so I have to add 2. So now my nitrogens are balanced, but now my hydrogens are not. I see 6 on my right side, but only 2 on my left side, so I definitely need to add a 3 here. So I have 2 nitrogens, 6 hydrogens, 6 hydrogens. Beautiful. All right, so now we have our chemical equation, so now we must draw this out. So we know that nitrogen has a triple bond, and then we're going to treat that with 3 different hydrogen species. So there's 1, 2, and 3, and then we have to create 2 ammonias. So here's 1 and 2. All right, so we have chemical equation. Then we've drawn our structures. Now we need to come up with our delta H reaction, just our base equation here. So bonds broken minus bonds formed. So the first thing we do is we absolutely have to break that triple bond, and then we need to break 1, 2, and 3 of our hydrogen-hydrogen bonds. Okay, then we're forming 1, 2, 3, 4, 5, 6 NH bonds. Okay, so now we need to plug in our values. Again, I hope you understand how to use that chart, because I'm skipping over that part here. So for our nitrogen-nitrogen triple bond, which actually you can see right here, is 945. Okay. And then we have 3 hydrogen-hydrogen bonds, which are 436. You probably have started to memorize that number, because we see that one a lot. And then we have 6 nitrogen-hydrogen bonds. We don't use this one as frequently, but that has a bond energy of about 391. Again, these are all in kilojoules per mole, okay? I'm just dropping them because I'm lazy. All right, so now if you put this in your calculator properly, you'd end up with something of negative 93 kilojoules per mole, which again makes sense. If you have to break a triple bond, you have to put a lot of energy in order to do this. So this would definitely be something that if you were able to do this, the driving force would be definitely so it's more stable. So I would expect an exothermic reaction. But again, if you're not there yet, I totally would not expect for you to know that, okay? Just make sure that you can write out that equation, draw the structures, and then come up with your delta H of your reaction, all right? So hopefully you're able to do this. Please note, though, for the way I have this drawn right here, I have determined the delta H of the reaction for 2 moles moles of ammonia, usually when I asked for this on an exam, I would say, what is the delta H of the reaction for 1 mole of ammonia? So I would expect for you to take this value and divide it by 2. And then whatever your answer is here is actually what the actual final answer would be, okay? So just please make sure you're reading the reading the problem, and make sure you're giving the answer that is asked of you, okay? Have a great week. Take care of yourself. Drink water.